So, for the next talk for this evening, this is a talk that is personally interesting to me, and I hope to you as well. I'm very much looking forward to it. Our next two speakers will be talking to us about how we can deploy GSM base stations over software-defined radio hardware. So very interesting things that we'll hear from them. So please welcome Vadim Yanitsky and Piotr Krysik. A big round of applause to them.
Introduction. So, hi everyone. This is the first talk ever at the Congress, so thanks for having us here. Let's start. My name is Vadim Yanitsky. I'm a researcher from Positive Technologies company at the telecommunication department. At the same time, I'm a Asmacom contributor. I had some background in web development, but this time is gone, and now I'm in telecommunications. Now I prefer to use C and Python, and this is Piotr.
Hello everyone, I'm Piotr Krysik. I'm working at Warsaw University of Technology. I'm generally a person that thinks that using free software is a good idea, and writing it is even better. So I created some small pieces of free software myself, and one of them is GSM. I will introduce it later. Another one is multi-RTL. It's software for synchronizing RTL SDR devices in order to make from them multi-channel receivers. So this is
okay. So we are going to introduce our work we have been doing for some long time, and in a few words we will show you how to run a GSM mobile phone on software-defined radio. And as you probably already know, our project is mostly based on Asmacom BB project. So we will introduce it in a few words, and we will tell you what's wrong with the currently supported hardware, and why our work makes sense. And finally, we will show you some demonstration. So let me ask how many people here used to play with Asmacom BB? Raise your hands, please. Not so much, but anyway, thanks. So, from my experience, when people hear about Asmacom BB, they basically imagine an old Motorola phone with always hanging firmware. So, what is it? It's not a secret for everyone that your phone actually has separate baseband processor that takes care about the network operation. No matter which operating system do you prefer to use, when you're sending a short message or calling to your friend, your operating system kindly asks the second baseband processor to do that. So a baseband processor is typically running some proprietary firmware, and as many other people, we don't trust this firmware. So the main idea of Asmacom BB project is to provide the open source implementation of phone-side stack of GSM. And the higher levels of this stack are typically represented by software running on your host site, PC, and the lower layer is layer 1, is firmware, which is running on some Calypso-based phone. And the implementation is more or less complete, so you can make some voice call and receive SMS message and so on. But at the same time, this project is not actively maintained at the moment. So you may ask me, why do I need this project for what for is it? And well, it depends on who you are. If you are a student or GSM beginner, it may become your best friend in practical learning of GSM stack. If you are some kind of security researcher or doing something related in GSM networks, you probably already know about this project, and I don't need to explain you. And of course, it mostly helps to debug existing Asmacom projects. So, yeah. And a few years ago, there were a few leaks of TI Calypso source code and documentation, and these allowed Osmocom researchers to reverse engineer the firmware of some old Motorola phones. And yeah, so the primary hardware for Osmocom BB is mostly Calypso-based phones, mostly Motorola C1, something like that. And such phones run custom firmware, which represents layer 1 of GSM stack, and this firmware interacts with the host software via serial link. And mostly the problem is that this firmware doesn't do much of things. It mostly drives a proprietary DSP. And what is the problem is that such hardware is not manufactured anymore, mostly. And the DSP, which is digital signaling processor, is not fully researched. So you still rely on a black box running open source software. And finally, this is not full open source implementation. And the hardware, this limits you in some ways. For example, you cannot operate in GPRS mode despite the hardware is capable to do that. So what happens if we try to replace a Calypso-based phone with something else? For example, what about software-defined radio? And what is software-defined radio? It is a general-purpose radio hardware. It's not limited to any particular technology or software stack. And so this means that it could be used for different technologies and protocols like LTE, Bluetooth, GSM, and of course GSM. So the good news here is that this is open source friendly. Many open source projects do support SDR, and many SDR vendors do support open source actually. And of course, software-defined radio is popular in scope of mobile communications, so you can run your own LTE network, for example, or run your own GSM network. You can even run LTE mobile site stack. But what about GSM? Can we run a mobile phone on GSM actually? And oops, yeah, this is actually when our work came to play. So do you remember this is general purpose hardware? So there is no screen, there is no keyboard, there is no SIM reader or audio subsystem. But in general, we are not going to create another open source user targeted phone. So then you ask me, what is it for? And mostly this inherits some IAMS from Osmocom BB project, and as mentioned before, it's mostly for education, research, and development. And this allows you to implement absolutely open source layer 1 implementation. This allows you to get another hardware platform for Osmocom BB. And yeah, let's turn back time and imagine that we are developing a software-defined radio platform for Osmocom BB from scratch. And from what did we start is here on the top of this picture, you can see the Osmocom application, which was previously used to connect the higher level applications and lower layer represented by firmware together. And the higher applications used to communicate via serial link. But in our case, we don't have firmware anymore, we don't have phone, and we need to communicate with software-defined radio somehow. So yeah, after a quick look at the source code of Osmocom BB, we found that it do use layer 1 control protocol, which is a custom but pretty simple protocol. And good news is that this protocol is already implemented in software of higher levels and in firmware too. And the problem is that Osmocom BB host applications do understand layer 2 frames, but not layer 1 bursts. So you need to implement some kind of burst encoding from, yeah. And Another problem is that host applications don't care about time division multiple access, and this is one of some basic technology in GSM. So we need to implement some kind of TDMA scheduler here. And Osmo BTS became our source of inspiration because both things already implemented here. So we separated the common part of Osmo BTS, which is actually Osmocom base station project. And we created a separate shared library called libosmo coding, cleaned up and documented some parts of code and extended with accelerated Viterbi decoder. And also we took some basic GSM structures like multi-frame structure or clock synchronization routines from Osmo BTS as is. And finally, now we have TRX Con application, and now we can communicate with higher level applications, but still we cannot communicate with software-defined radio. We can receive birds, perform encoding and decoding for them, but we cannot directly communicate with software-defined radio. And there is a TRX protocol, which was first introduced in OpenBTS project, and it's still used by Osmo BTS to communicate with transceiver. And basically, it assumes 3 UDP sockets, one for resource management, another for frame clock indications, and other for actually for bursts. And so, okay, we implemented these two in TRX-Con applications, and now both Osmocom BB and Osmo BTS projects do support TRX interface. So maybe connect them together for early development and testing without actual hardware. And yes, of course, we can do that. And so welcome Fake TRX Toolkit is a set of tools written in Python and mostly used for debugging TRX interface. And the most interesting application here is Fake TRX. It works, it allows you to connect TRX-Con directly to Osmo BTS application. It acts like a proxy on the level 1, so you don't need any hardware to interact with your open source network from open source stack, mobile site stack. And what is the purpose of this tool is, for example, you can learn whole GSM stack without hardware. You can perform simulation and stress testing without hardware, and of course you can test and debug other projects. And yeah, so we need the last part, which should directly communicate with transceiver, and what these applications should do is to perform downlink burst detection and demodulation. It should be able to perform uplink burst modulation, and yeah, it should follow TDMA time system of GSM. And of course, finally, it should talk via TRX interface, which is currently supported by TRX-Con application. So, yeah, there are 2 programs which might fit our requirements, and one of them is Osmo TRX, and it's still used in Osmocom project. Basically, it's designed to act as a BTS, and it could be used, but the source code is heavy mix of C and C++, and you need to understand the whole infrastructure to make some little modifications here, and probably we will take care about Osmo TRX in the future. So also there is GR-GSM, and this is GNU Radio out of 3 module to play with GSM, so it's modular, easy to modify everything as you need, so why not to try this too? And yeah, this is why I contacted my friend Piotr to continue work on that direction together. So, yeah.
Yeah, the part of my work was implementing the burst transceiver for the GSM. And it is based, as Vadim said, on GR-GSM, which is relying on GNU Radio. The whole GR-GSM project was started from a part of APRO project that years ago in 2009 I added to APRO project. It was called GSM receiver, but it is now much more from just a software for passive receiving bursts. It also does demultiplexing, decrypting bursts. It has GNU Radio blocks for decoding different logical channels for filtering bursts. And there are also out-of-box applications demonstrating how to compose these blocks into working applications. There is application for live monitoring, GSM broadcast channel, decoding different logical channels and analyzing them in Wireshark, and also for searching BTS as active in the area. So what was the initial project status? It was that we had the whole receiver, but what was missing was, of course, whole transceiver chain. And what was to do was to implement GSM burst modulator, then figure out how to synchronize the transmitted signal coming out from this modulator with signal received from the base station, and then we actually had some constant time offset that needed to be corrected, and in the end we had to verify if the signal transmitted the radio output is the right one, so we don't interfere with anyone's license bands. So very short introduction of GSM. Signal at the UM interface, the radio interface of GSM. It uses time division multiple access with frames containing 8 time slots. Each time slot carries one GSM burst. It's kind of a GSM packet. And these packets are usually modulated with Gaussian minimum shift keying modulation. And the position of each burst is precisely defined by the frame number and time slot number in which they should be transmitted. So the first task was to implement the modulator, and it was actually quite simple because all of the building blocks were already in the GNU radio. So I just had to figure out how to connect them together to make a working GSM modulator. There is already GMSK modulator in GNU radio, and then with some blocks, we're calculating some blocks together, you can perform differential encoding, connect them together and hope that it will work, and yeah, it should work actually. And the other task was to synchronize the transmitted and received signal, and this wasn't as easy, but in the end the implementation isn't very large for this. So we have following task. We have burst coming from the upper layer. They have frame number and time slot number, and then we have to somehow transmit them in precisely defined moment in the whole TDMA structure. So for this, very helpful is hardware clock that is in the inside of the software-defined radio that we use. This is USRP. It allows for transmitting at precisely defined moments, and the received signal is also tagged with the current time. So you have time attached to a sample, and then the receiver, based on this metadata, can track current time. And if it receives a signal coming from base station, it can synchronize with this signal and associate reception time to frame and time slot number. So this pair of information is then used for performing conversion of frame numbers and time slot numbers into transmit time tags that are added to the bursts that are for the transmitting. And based on this information, after the modulator, the bursts are transmitted by USRP at precisely defined moments. So after this, finishing this task, we still had some unknown but constant delay caused mainly by signal processing algorithms like, for example, low-pass filtering, and also by SDR hardware. So we needed to take it into account, and how we did this is here. So we have a signal coming from the base station to the USRP. The output of receive chain, we have bursts. These bursts we connect back to the transmit chain, but with adding some known delay of some known number of frames. And then we retransmit this signal at some frequency close to the received signal frequency. We then record both signals, the received signal, which contains both signals, channelize the received and the light signal, remove no number of frames of delay from the delayed signal, and what is left is the unknown but constant delay between the both signals, the received and transmit by us. And this we can measure with use of cross correlation. It should appear in here. We can measure it with use of cross correlation, and it will give us the shift from the 0, and this shift of the peak of the correlation from the 0 position is actually our delay that we have to put into take into account in producing the transmit tags. So then we had to verify the transmitted signal amplitude, and normally programs like Osmo BTS or Osmo TRX are transmitting constant stream of samples, but for mobile station it will be kind of lame to do that, because we would have to transmit constant stream of samples when mobile station has to transmit something only from time to time. So we actually used USRP's burst interface to transmit burst for each GSM burst, and it has many advantages, like we transmit when we need, and it's easier to resynchronize the transmission in case of transmission problems. But there are some drawbacks, and here is how signal amplitude should look like for the GSM. There are some guard periods when the signal amplitude goes down, but then it's kind of constant. But this is what we got, and where the hell 300 microseconds of our bursts were gone? So after some looking for the answer, it appeared that this problem appears only on USRP's B210, and it can be limited into this, that it appears only when we are transmitting and receiving on the same side of the device. And it also appears only when there is no connection between active pin of the transmit port and the signal ground. So if we avoid this, we can have much better signal amplitude. But then, what is that thing in front of my burst? So what is this? After some looking, it appeared that this is the end of the previous burst that appears at the beginning of the next burst, and it is probably the result of growth delay of the USRP's FPGA processing chain. And and it can be avoided by just adding zeros at the end. So if I would know at the beginning, I would just do that and not lose some time on this. And in the end, what had to be done was verifying transmitted signal spectrum with spectrum analyzer. And when you are connecting antenna to the SDR device, you should take into account always the fact that it might not produce the ideal signal. And for example, here for USRP B210, there is a signal with amplitude of minus 13 dBs from the main signal on the third harmonic. So you should always put analog low-pass filter, especially in case you are using a wideband antenna. So after applying the filter, you get something like this. So at this moment, my part was working, I think, but to check that, we had to wait for the demo done by Vadim.
Yeah, thank you. So when we finished more or less working implementation of that transceiver, we get something like that. So finally, we can now communicate with software-defined radio through the application called GSM TRX. So we can not only communicate with our open source stack represented by Osmo TRX and Osmo BTS, but also with different base stations. So yeah, let's try to show some demo, but we have some limited time. And I need to put it here. Yeah. So first thing we need to run is actually our transceiver. Yeah, it will start. And then we need to run our TRX cone, which actually acts like a bridge between transceiver and Osmocom BB applications. And finally, we need to run some Osmocom BB application, for example, mobile application. Yeah. And what's happening now that it just synchronized with base station of this local network. And now we can try to register here, for example. Yeah. This is classical things. We need to put our virtual SIM card because at the moment we don't have any direct SIM card interface, so yeah, let's try. And what's happening now, we just performing location update request in GSM network. And let's see. Yes, and we just registered on that network. And what we can do here is to perform some basic operations, like we can request for our number. It's simple. So yeah. The implementation is not so stable, so feel free to contribute our project. And yes, this is our virtual extension, so we can try to send SMS message to ourselves. It we should receive it back for example, this way. So yeah, we got a channel. And oops, let's try one more time. Okay, yeah, and we got it back. Yeah, thank you. And finally, let's try to call somewhere because we have some basic sound integration, and I hope it shouldn't. Yeah, let's try to call some testing number, actually. Finally. So, we need to switch back to our presentation. And yeah, the current project status is here, and it's not so perfect as I would like to see. So, what have we achieved is now we have full open source GSM layer 1 implementation. And so you don't need to hunt for Calypso phones anymore. You feel free to use software-defined radio. You can use any frequency you want. For example, you can run your network in Wi-Fi band and call in this network. We are close to the future GPRS implementation. And for example, we can do some things like try to integrate non-GSM audio codecs like Speaks or Opus here. And of course, this is the wind of change for Smacom BB. This is a new hardware platform for that project. So yeah, thanks for your attention and feel free to ask your questions.
So thank you very much, Vadim and Piotr. Unfortunately, we're out of time, so we don't have time to do a Q&A. Hopefully you can stick around and people can maybe approach you if they have any questions. So again, a big round of applause to Vadim and Piotr for a great talk. Thank you very much.